Very much, Peter, for the introduction, and thanks to the organizer for the invitation. As Peter mentioned, so in the context of this ACCR project, heat and electricity storage, basically we're working at PSI on the development of advanced catalysts and devices for CO2 reduction. What will be focused today will be most on these devices for CO2 reduction. We have what we want to do with such a process. We want to store the surplus of renewable energy and to reduce the CO2 gas emission from different sources. By electrochemistry, basically we can transform the CO2 in chemicals or other liquid fuel production, which further can be used to produce other energy and CO2, of course, and then, going back to recycle the CO2. With such a scenario, so we want to store energy, to reutilize the CO2 emission, minimize the atmospheric CO2, and for sure close this carbon cycle. But electrochemistry is not, it's a good technique, but it's not magic, so all these processes, need to be think a bit, and they are taking place in a device which is called co-electrolyzers. To design such a device, so we start with, we need a design. So we start the project in 2040 with this ACCR, and we did a bit of, let's say, pioneering work, because at that time, we didn't have any device or any concept, to work at this level. Then, we need to prove that our concept works. A lot of optimization needs to be done, and also we're trying now to progressive upscaling, up to 1 kilowatt, such a process. And the final goal being to have a co-electrolyzer which will be integrated in the energy and integration system, and so this AC platform at PSI. But before going there, so we are here, so we managed to have now a design of co-electrolyzer and the proof of concept. And we are continuing working on the optimization and progressive upscaling, and hopefully after 2020, to see our dream, coming through and having, a real co-electrolyzer integrated here. But what exactly is this co-electrolyzer device? So we have, it's an electrochemical process which couples the water splitting with the CO2 reduction. So generally, maybe we speak a lot during the morning about this hydrogen production, this green hydrogen production, and this generally takes place in a water electrolyzer. So we have a cathode when the hydrogen is produced, and an anode when the water is oxidized. So what we need here, we take the hydrogen and use it, for example, for mobility. In a co-electrolyzer, it's basically the same concept, just that at the cathode side we also fill, CO2, and we are trying, to reduce it in CO and hydrogen, which give this nice mixture, intermediate mixture of syngas, which further can be used in a Fischer-Tropsch process and produce other chemical or liquid hydrocarbon. The reaction taking place here, it's what we want to have at the cathode, it's the CO2 reduction reaction. And this, it's a bit of a complicated reaction, so can take place in different manner, involving different number of electrodes, different reaction mechanisms, and which can be reduced, the CO2 can be reduced here to different products like CO, methane, alcohol, and so on. This is what's happened in theory, but what we know so far from the practice is that, this reaction here, so the reduction of CO2 to CO, it's, let's say, valuable also, it's more easy, and it's valuable also for an economic point of view. So that's why for the rest of the talk, we'll focus on this, only on this reaction, and not on the other aspects. However, there are still challenges to be done here. So, we need to find selective catalysts for this reaction. We need to improve the kinetic and also to suppress the hydrogen evolution, which is in competence with this CO2 reduction. And this is not everything we have to do. It's also we need that the reaction is taking place. Also, we need a couple of conditions to be there. So, like pH, temperature, and also nature of the reactant. Now, when we have to upscale such a process, there are few problematics. So I was mentioning that, okay, the pH, it's necessary to be maintained at a certain value that the reaction is taking place. When the studies are done in the literature, they are done in, let's say, in a more defined condition, and generally in aqueous electrolytes. And in that case, the pH is relatively easy to be maintained. But in such electrolytes, the CO2 solubility is very small, so we are in the range of 30 millimolar. And this will result in very low, for sure, efficiency and very low current density that we can achieve. So this is not a solution to be directly transferred for a, let's say, laboratory phase to a co-electrolyzer. So that's why we need, let's say, device engineering which can operate with CO2 in gas phase to reach this, okay, let's say this solubility limitation. And so far in the literature, okay, the state of the art, there exist two major type of reactors. So it's so-called gas liquid reactor. This one is a membrane electrode assembly, and they have the particularity that the CO2 can be fed here in gas phase at the cathode, but the pH is still maintained, with the liquid phase. So we have a flow of electrolyte between the cathode and the membrane. And this, okay, you can obtain nice result with that, but still the reaction, the CO2, it's limited by the solubility in this phase. So our idea was to design a gas reactor on which we have the reduction is taking place directly from gas phase. In this case, okay, so we don't have solubility problem, but it's a bit more complicated because we still need to maintain a pH in gas phase. So this is what is complicated in this system. So our goal with such a device was for sure to reach high current density, high energetic efficiency, and good product selectivity. The approach was to use gold black as catalyst, cathode catalyst for CO2 reduction, and the pH will be maintained by different ionic exchange membranes. So we take basically the commercial available one. The measurements were done, okay, in this type of setup. So we have here a small electrochemical cell, which is something like 0.5 square centimeter. We have cathode, membrane, and anode, and the reaction products obtained at the cathode side can be quantified online by mass spectrometry. So we can follow what's happening into the reaction online. Okay. So now let's see finally the result. So we start, to build such a reactor by using commercial available membrane. So what we have so far, we have from the fuel cell or for the electrolyzer technology, we have this Nafion membrane, and also we have for the alkaline system, we have something like Fumasep, membrane. When you look at the current density that we can obtain at the cathode, for sure, in acidic condition, we can drive a lot of current through this membrane. However, this current it's mostly transformed in hydrogen and not into CO. So we have here, when you observe very low CO selectivity, meaning that, okay, this condition is not really favorable for the reduction of CO2. However, in the alkaline, when you use alkaline membrane, here we have for sure lower current density, but we manage, okay, in a better manner to reduce the CO2. So the selectivity are increase compared to the acidic condition. And that's why we choose, okay, this system, okay, even if it's not energetic efficient compared to the acidic one, we choose to use this system. However, during our study, we figure out that also this system is far to be ideal, because we have some problem in such a system. So when you feeding CO2 and water at the cathode, here we have this type of reaction taking place, and both will generate this type of ion, so this OH minus ion, which the problem is that, okay, in the strong CO2 environment, they will be carbonatated in bicarbonate and carbonate. And this will be further transferred to the membrane, so we'll not have only OH going to the anode side, we'll have also carbonate and bicarbonate. And this will be oxidized here into oxygen, but also into the CO2. So basically, when we make the balance of such a system, we end up by having, for example, for one molecule of CO2 reduced here, we generate 2 molecule or 4 of CO2. So we are not, okay, what we are just putting electricity to produce, to double, the CO2. So it's something that, okay, it's not really what we target. And we measure here the gas to confirm that hypothesis. We measure the anode gas composition, and this is quite clear that for a given a different current density, we have a volume of oxygen and the double of volume of CO2. So this confirms that, okay, we have this reaction, only this reaction is taking place at the anode side. So we produce 1 oxygen and 2 CO2. So this is what we call like a pumping effect of the CO2 to this alkaline system. And now, okay, we're a bit limited at this point, how to manage. So the acidic conditions are not working because they're not selective, and this one, they are just pumping, the CO2. So to propose an alternative solution here, we come with this bipolar membrane system. And in this case, so we keep the alkaline side of the membrane at the cathode to maintain the acidic condition, and the acidic one to the anode. And what's happened here is that all the carbonates that are formed in this alkaline condition are, let's say, neutralized at the interface of the membrane, creating water and CO2. When we compare the performance of such a system with the alkaline one, so we have a slight increase of the current density, and we maintain, let's say, in a similar range the selectivity of CO, which is quite normal because we use the same catalyst and the same alkaline condition. And here, when you look at the transfer of the CO2 to the anode, we see that, okay, there is quite a big difference. We still transfer CO2, but probably most by diffusion and not by an electrochemical reaction, which was the case in this full alkaline system. We are quite happy with this result, but we find that, okay, the limitation here is that, okay, if you have water and CO2 formation at the interface, the membrane can delaminate, and this, during a long-term operation, it's not something that we want to have. And then we come with another solution. So in this case, we use here the cathode with an alkaline ionomer, and we just spray on top of it a layer of alkaline ionomer in a certain manner that we can keep the porosity of the cathode, and this is put in contact with the Nafion membrane. So in this condition, we can stop the CO2 transfer because everything will be created here at this interface. The CO2 can escape through this porous structure and not being transformed to the anode side. And for sure, using just the Nafion membrane will lower quite significant the overall resistance of the cell. And this can be seen, okay, for the result that we obtain. So we increase considerably the current density of such a system, and also we manage to keep similar CO selectivity on the cathode side. And for sure, what's happened at the anode side, here just at 100 milliamps by square centimeter, we managed to see a bit of CO2, but basically this effect is of the CO2 pumping is suppressed with such a configuration. So yeah. This is what I present so far, where the cathodic curve, just the current that we registered at the cathode side. But what's happened when we have a full electrolyzer? So when we have a system on which we have iridium oxide on the anode side, so we do also this oxygen evolution. So in this case, we see that, okay, with this new configuration, we managed to achieve like 200 milliamps by square centimeter with 1 volt difference here from the other system. So we are like at roughly 3 volt of cell potential. We are obtaining, 200 milliamps by square centimeter, which is a good result for this co-electrolyzer operating at low temperature. Okay, so I was mentioning at the beginning that, okay, we want high current density and low, let's say low energy consumption. And also, high CO2 reduction rate. So far, our selectivity are a bit slow, are not very high, so we're in a range of 10 to 12% of CO selectivity. So there is place for improvement here, and we're trying to understand, okay, because generally when we use gold catalyst, there is reported in the literature, and we also measure in our, let's say, defined cell activity of up to 90% of CO. So this is also what's happened with our catalyst. So if you are in this potential range between minus 0.4 and minus 0.8, we can have a lot of CO production. Then, okay, what's happening in our gas phase? So if you plot the potential at which our cathode works, and the Faraday coefficient that we obtain, and we compare with what we obtain in this liquid phase, we see that we are in a different operation range of potential. And this, okay, what we have to do now to increase our performance, it's either to operate our cell at lower over potential, either to find a catalyst which is, let's say, produce CO on a larger potential window. And yeah, this is something that we are currently working on. Then another, let's say, critical aspect for this system, it's for sure, the stability of such a system. We run our cell, let's say, for 21 hours at 50 milliamps by square centimeter, and here we can see that during time the cathode potential it's decreasing, and also we have a complete drop of CO after 5 hours, and this is okay, not what we want to see. However, we understand that, okay, this loss in CO selectivity doesn't come from the cell component. It's just a matter of water management in the system, because as I say, if you remember the cell configuration, we produce water at the interface between the alkaline and acidic membrane, and this water is accumulated into the cathode side and blocks basically the surface of our cathode. And in this case, we'll produce only hydrogen after 5 hours of operation. However, if you stop the cell and we dry the cathode out, we see that, okay, we recover also the potential and also the CO selectivity. So this is also a point on which we are currently working to, let's say, to equilibrate this water balance into the system. So this is, let's say, where we are with our research on this co-electrolyzer. So what are the highlights? What we achieved so far is that, okay, we have a design of an efficient co-electrolyzer and we have a proof of concept. So this is this new configuration. Okay, it's quite a unique design, and we managed to have a patent application on it, and also to generate, let's say, new idea for this CO2 business. So with this type of configuration, using this pumping effect, we realized that we can concentrate and store electrochemical CO2. And this was a project that we wrote last year, and it was granted by Shell. So we'll also work with such a system on the separation and concentration of CO2 starting for next year. And what we are currently doing, so okay, we have, as I mentioned, we have a lot of optimization to do on the system, which consists of, for sure, in cathode catalyst. So here we have a collaboration with Peter, so to work with this silver-based catalyst. Also on the MEA, we'll need, new anionic polymer, so we have different collaboration. And for sure, for this progressive upscaling up to 1 kilowatt, we are building now a test stand when we can test 25 up to mini stack level, co-electrolyzer, and hopefully by the end of the project we manage to have a stack to be integrated. So yeah, thank you for your attention, and thanks my colleagues for the work. Thank you.